Hello, and welcome to the ACP Automation channel, and to video number 1 of this multi-part set. In these videos, I would like to look at how Siemens PLCs can take in an analog input and scale it to engineering units, then to be able to take the normalized value and unscale it back to a voltage or a current. What do we mean by analog input? Well, in essence, computers can only work with ones and zeros, or ons and offs. These signals in the PLC world are known as digital signals. So for example, a push button can be pressed or depressed, a lamp can be on or off, a valve can be open or closed, and a heater could be on or off. These types of signals are great if we only have two states, i.e. on or off. But what if we want to know quantitative things, like what's the temperature, what pressure is in something, or how fast is something spinning? Also, like before with our example of digital devices, what if instead of wanting to know if a button was pressed or depressed, we might want to know what force is being exerted on the button in grams, how far open a valve is in percentage, or to be able to control the brightness of a lamp. These types of measurements are known as analog signals. They are constantly changing values, and to be able to quantify them, we give them units of measurement. So for example, the intensity of a light source can be measured in lux. The temperature of a room can be measured in degrees centigrade or degrees Fahrenheit. To measure these physical quantities, we need to use a sensor which can convert the physical quantity, i.e. heat, into an electrical signal like voltage or current, which can be detected by a PLC. The PLC will need to have an analog interface present in order to process the electrical signal being received. Here is a graphic of how an analog signal may be represented. The value being measured is on the y-axis, so this could be temperature, speed, etc. This is plotted with respect to time on the x-axis. So, to be able to measure these values in a PLC and display them as meaningful units, we need to scale the analog signal from the sensor. In order to do this, we need to know some information about the sensor, like is it voltage or current, the range which it can detect, the output characteristics like is it 0 to 10 volts, 1 to 5 volts, 4 to 20 milliamps, etc. Once we know this information, we can start programming. I intend to split this topic over 3 videos and hopefully show how an S5 PLC, an S7 Classic PLC, and an S7T Portal PLC can scale an analog input and then take a normalized value and unscale it back to binary to be written into an analog output. This video will focus on how an S5 PLC can process and scale analog signals. So as can be seen here, I am using an S5 95U brick type PLC. These PLCs have 16 digital inputs here and 16 digital outputs here on board, as well as 8 analog inputs and 1 analog output, which can be accessed via this 15-pin connector here, not to be mistaken for the 15-pin programming port here. The analog signals here are 0 to 10 volts and are represented by 10 binary bits, 0 to 1023 steps, or 0.0097 volts per step. This means that for every 0.009 of a volt you put into the analog input, the binary value will increment by 1. So for example, if you want 5 volts to be output from the analog output, you could divide 5 by 10, which gives 0.5, then multiply this by the maximum binary output, which is 1024. This gives a result of 512. So if you write a binary value of 512 into the analog output, you should get 5 volts. Siemens S5 offered the user 2 ways of getting these signals in and out of the PLC. The first was by directly writing or reading from the analog output/input. The second way is by using the scale/unscale function blocks FB250 for scaling and FB251 to unscale the analog signals. In this video we will look at the scale/unscale blocks and how to parameterize them. Here I have a new project opened up in the Step 5 editor and PB1 loaded and ready to be edited. Firstly, we will load a new FB call, select F6 to edit, then Shift F2 for blocks, then F1 to jump unconditionally to an FB. This means that this instance of the FB will be called once every scan. When the block call is loaded, the editor will want us to type in an FB number. So type in FB250. This is the scale analog input function block. It's worth noting at this point that this block is not part of the Step 5 IDE and will need to be either downloaded from the PLC or copied across from another project in order to use it. Also worth noting is this block is not present on all models of PLC. For example, the FB does not exist on the 928 CPU for the 135U PLC. So, once you have made a call to the block, the editor will want you to parameterize the block. The first parameter you come to is BG. As with all Step 5 function blocks, the input and output parameter names only had space for 4 characters, making them quite cryptic. Parameter BG takes a constant fixed point number, or integer, which represents the slot number. Set the slot number to 8 if the analog input to read is on board. Otherwise, this number will be the number of where the card is in the expansion rack, i.e. 0 if the analog input card is the first card after the processor. The next parameter is KNKT. This parameter takes a data type of constant byte, with the first byte being the channel number and the second byte being the channel type. Our channel is channel 0, so enter 0. Set the channel type to 4 for unipolar representation if using the onboard I/O, as they are only 0 to 10 volts or 0 to 20 milliamps. Next we have OGR, which is the scaled upper limit, and UGR, which is the scaled lower limit. Both these values accept a constant fixed point value or integer. These values are what the 0 to 10 volts will represent. So if you wanted to scale the value from 0 to 100%, then set OGR as 100 and UGR as 0. So when 5 volts is applied to the analog input, the scaled value will read 50. INS is the next parameter we come to. INS is Boolean and will accept a flag bit, for example. If this is set to 0, then the block will read from the process image. If set to 1, then the block will read directly from the I/O. If you want to read the analog value cyclically into the I/O image, then you will need to set the appropriate parameters in DB1. So for this exercise, I will read the values indirect, so I'll need to set this to 1 when we come to test the program. In this case, I will use input 32.0. The next parameter is XA. This is where the scale value will be put into. In this example, I will use flag word 0. Next are two error bits, FB and BU. FB will switch on when a wire break is detected or the wrong channel type has been programmed. BU is the range violation bit. This will switch on if the input value exceeds the input limit. So for this I will use Q32.0 and Q32.1. So now we have the block parameterized, let's insert what we have done. Enter the modified segment, enter the modified block. Already in the file override? Yes. In order for the PLC to execute our program block PB1, we will need to call program block 1 from OB1. From the editor tab, select step 5 block and press enter. Type OB1 and press enter. Now press F6 to edit, Shift F2 for blocks, F4 to jump unconditionally to program blocks. Type in here PB1, then press enter, then press insert to enter the modified segment, yes. Press insert to enter the modified block, yes. Already in file, override, yes. Now we will need to download this to the PLC. Let's go across to File, Blocks, Transfer. This is where we're sending the program from. So this is the program file, and we're going to send this to the PLC. And the block list, we're going to put A, which means all blocks will go in. So let's press Insert. So FB250 is part of the system and therefore cannot be downloaded. So press yes, and FB251. Then we press Escape. As step 5 displays in hexadecimal, it would be nice to display the scale value as a percentage 0 to 100. Let us go to Status Variable and press Enter. In here we can see the status of variables and select how we want to display them. Let me type FW0. This is where our scale value will be written to. As can be seen, KH is set automatically, which is hexadecimal. We want to display it as an integer. Step 5 uses KF, constant fixed point, as an integer value. So let's type KF into there. Enter. Let us also see the status of input 32.0. This is the input which selects between direct I/O access and cyclic I/O image. Q32.0 and Q32.1 are the header bits, so let's display those as well. Q32.0 and Q32.1. Now press F6 to activate the status. As we can see, our scaled value is displaying 0. Once I turn on input 32.0, the processor will read the analog value directly from the I/O. Input 32.01. So now, when I turn the potentiometer, we can see the percentage rising all the way from 0 all the way up to 100. You may notice that Q32.1 has turned on. This indicates that we have overflowed slightly. And then if we turn the pot all the way back, we can see it goes all the way back down to 0. Okay, that comes to the end of this video. I hope it has helped and you've enjoyed it. Please remember to like and subscribe. Thanks for watching. Bye.